Hi, if you're a mechanical test engineer and you use sensors to make a better product through validation, this video is for you, because Jeff and I are going to show you, using this torque test for a power drill, how NI hardware and software can help you say yes to all of your really good ideas for your test system. All right, Jeff, let's just jump right into it. Let's test the torque on this power drill.
Let's do it. Here we go. We're going to spin this thing up, and then we're going to apply some torque through this linkage with a brake.
Let's do it.
So we're going to spin this thing up, and then we're going to start applying brake. And there we go.
So I heard the clutch kick in. So it sounds a lot like the drill that I have at home when it bears down and then the clutch kicks in. And so this is a great example of a test system that a manufacturer of a power drill could use to characterize their torque profile across all the different clutch settings, or maybe cycled through this to see the durability of their drill, right?
That's right.
Good examples?
Yep, exactly.
Okay, well, to get a better look at the mechanicals on this demo, let's go ahead and take the top off, and then we can kind of poke around a bit when it's safe.
Sounds good.
Okay. All right, Jeff, now that we've taken the top off of our torque tester, can you walk us through the components?
You bet. Let's start with the mechanical system and walk through each component one by one so we can understand what we're dealing with.
Okay.
So the main event here is our consumer power drill. So this drill is an 18-volt system that you typically find at your big box store.
Yep.
And we've got this connected through a coupler here to our dynamic rotary torque sensor. So it's a cool sensor. It gives us a variety of information, including the RPMs and the torque that we're applying from the drill.
Gotcha. So this big red box that's the torque
sensor. Big red box is our torque sensor.
Okay.
And then on the back side here, we've got a magnetic particle brake. So what we're doing with this is we are loading down this consumer power drill so that we can see what the max stall torque is.
Okay.
So we've got a controller. Once we get the lid back on, you'll see the controller is going to apply some current to this brake, and then that's going to resist the rotation from our drill. Okay,
so you can spin the drill just like a normal drill.
Yep.
And then this is the brake that applies the load to it, because we don't have nuts or bolts or anything up here. And then the red box in the middle is going to tell you how much torque is impacted on the drill at any given time.
Exactly. So load cells inside of here, we're going to see what rotational torque we're applying to the shaft in this linkage.
Okay, so you've talked about a torque sensor, but I see some other sensors and wires going on.
You bet.
Walk us through all the measurements going on.
So while the core measurement is torque, we want to get some other auxiliary information so we can evaluate and validate the drill performance.
Okay.
So first of all, as you can see on the top here, we've tapped into the housing of the drill. We've got an accelerometer, a 50G accelerometer.
Okay.
And this is going to see what sort of instantaneous and potentially other types of acceleration that we want to analyze. In addition, we want to make sure this system is safe and we're not operating it too hot. As we start to torque this thing down,
probably a good idea.
Yeah, it might get a little unsafe. And so we've opened up the housing of the drill. You can't see it here, but there is an adhesive type T thermocouple that's adhered to the motor housing itself, so that we can see how hot this thing is getting.
Okay, so we got vibration to see, is it comfortable while you're using it?
Right.
We've got temperature to see, is it getting too hot and we might need to shut the test system down.
Right.
Okay, what else?
Lastly, rather than modifying our power drill battery, that might be a little unsafe. What we've done is we've tapped into the circuitry inside the charger base. So there's a couple of things that we can get from that. For one, we can see the bulk pack voltage as this is sitting on the charger. So we can see how does the battery voltage fluctuate as we operate the motor.
Okay.
In addition to that, this battery charger and the battery have a thermistor circuit that we can tap into from the back of the electronics here.
So you're getting temperature both on the drill, but then also from the battery.
Right. So rather than tapping a sensor into here, we can tap off the back of this charger. And rather than plug that into AC, which might interfere with our ability to measure the thermistor, we've actually used a current output module to excite the sensor in the battery through the charger, and then measure the voltage with our DAQ system here.
Okay.
So that gives us some safety metrics so we can monitor the battery and the drill temperature.
Yep. Okay, and I mean, I noticed that we've got a full CompactDAQ chassis here.
Right.
And this is kind of going back to when I said, hey, any good idea you have, the NI hardware helps you say yes, right? So I imagine as all of these sensors came up in conversation, it's well, yeah, we could do that. It's just what module do we need, right? So can you maybe walk through some of these modules and
you bet.
Talk about what's plugged in?
You bet. So first of all, the main event here was the torque, and really not just torque, but we know this sensor gives us RPM.
Right.
So one good idea we had is, what if we could correlate the vibration from the motor with the RPM so we could do more advanced analysis post-processing? We do things like power spectral density, things like that. In order to do that well, we needed to tap into the RPM that's coming off this sensor. So one cool thing about the C-Series is typically to get RPM off an encoder or something that's going to give us a pulse train with pulses per revolution, you're going to typically have to have a 5-volt pull-up circuit with a pull-up resistor and add all that circuitry external to your DAQ.
Extra work.
Pieces. And so what's cool here is we've got a counter timer module, the 9361, that we were able to add. And what that allows me to do is not only give me the pull-up resistor, but it also I'm powering the sensor through the module. And then I've configured the module to provide that 5-volt pull-up resistance and that supply to the sensor. And then I just configure it to say, give me 120 pulses per revolution, convert that to RPM.
Great example. So you got the torque sensor and you're like, hey, can we tie into this to get RPM?
Right.
And the answer is yes. We just need this one counter timer module and then sounds like some software processing to get the pulses per revolution. Great.
And then a second good idea we had, really, to keep things safe is if our motor temp or our battery temp get too high, we need to make sure we shut off DC to the battery so we don't burn the facility down or burn up potentially an in-development tool.
Sounds like a good idea.
Right. So what we did is we added not only are we monitoring these temperatures, but we've configured the software in a way such that we can use an electromechanical relay. And we're sending 12 volts through that to energize our safety relay. So we've got an ice cube relay down here.
I saw that, yeah.
And so we can energize that when the system is in a healthy operating condition. And then the moment that we detect that, hey, we're outside of our critical temperature limit, we can de-energize that coil and shut off DC from here to the drill.
Another great example. It sounds like that good idea maybe have come from safety and compliance.
Right. We actually had to do that. Our hand was forced, but we could say yes to that comfortably and make sure that we operate this thing safely.
Absolutely, that happens.
So really, what's cool here, from my perspective on the hardware side, is really a versatile system that, as an engineer, I can really achieve. I can say yes to all the different types of sensors I might encounter in a physical systems test like this.
That's great. Okay, let's put the top back on, and we'll switch over and talk about some software.
You bet.
Cool. All right, so we've got the safety shell back on, and we're powered up. Jeff, you walked us through the hardware and all the sensors. Can you tell us a bit how those sensors map to the software that we're looking at now?
Yeah, let's take a look. So what you're looking at here is the screen we just showed you while we were running the torque test. And on this screen, this is similar to what you'd find on maybe an operator's screen or an HMI. In this case, we've got a variety of sensor inputs that we're displaying for the user to see. So let's just do a tour of this screen. So you can see here we've got, on the left side of the screen, you've got battery temperature and motor temp. And as we described on the mechanical system, those are the two critical temperatures that we're wanting to monitor for safety so we can shut the system down.
That's right. Those were tied into that safety ice cube breakthrough.
Right. So you can see them live. They're updating. And again, one of these is a thermocouple. The battery temp is a thermistor. And we're just displaying those on a few indicators. In addition, we want to see what the bulk battery voltage is that we've tapped from the charger using some solder sleeves. So in this case, we can see the actual battery voltage and we can see that fluctuating with time. In addition, we want to see what our safety relay status is. So we've got a relay control indicator that says we're ready. There's no critical temperature event. We're ready to test.
So that's essentially like open or close.
It's open or close. So right now it's closed. We're energizing our coil and DC is flowing to the tool.
So
we're ready to test.
Yeah. Good as green. All right.
Good as green. In addition, we've got a sort of a notional diagram just to help you understand how this system is actually physically wired in a notional sense. So you can see that there. That's just a simple image that helps a technician understand the system a little bit better.
Yeah, it looks great.
In addition, when we start to actually spin up with some RPM, we've got a little status indicator that tells us, hey, we're actually logging, we're running. You've triggered an event and we're gonna capture the data at channel rate.
And are you capturing the data from all the sensors we talked about?
Yeah, everything is being captured, including all their metadata. So if I've configured scales or offsets, any sort of calibration, I've even got serial numbers being logged as metadata along with my data file. So I can search that, I can see who operated the test, what time, what hardware they were on, what the calibration status was, all that info.
Oh, that's great. So you can tie the hardware specifically to a test run in the data set.
Exactly. Okay. And then over here on the right side, you can see some of the more dynamic signals like the main event here, torque and RPM. So as you can see, we've got some gauges here that we can see live how much torque we're producing and how fast we're spinning the drill. In addition, we've got some instantaneous vibration in terms of G that this accelerometer is picking up.
Oh, that's great. Now, I want to call out that, this might be the case where, or the situation where we would normally say, hey, show me the code. Let's look at the block diagram. But this is not LabVIEW. This is a software product called FlexLogger, right? This is our no code, low code. It's actually no code application software for building test systems and logging heavy applications.
That's right. And what I like about that is I don't have to be an expert at the DAQ-MX API to program this system. I can really just get up and running, configure my sensors to my physical channels, and get running. So really no code here. And let's take a look.
Yeah, take a look. Let's do that. And how long would you say it took you to put this software together?
Surprisingly, this was pretty quick. This took us a few hours to configure the channels. So the bulk of the work is really making the system operate physically and safe to operate. And then really this just comes in here, we configure quickly, and we're up and running.
Oh, that's great.
Right?
Okay. Yeah, so let's walk through some of the, just maybe call out a couple of sensors.
Sure, we'll call out some of the interesting ones here. I'm gonna hide some of the unused channels. And we can see a listing of our different modules that map to the physical system that we have here in the CDAQ. So one of the interesting ones that I want to call out is how we've configured the RPM sensor through that open collector.
That's right.
So when we say no code, we really mean we've configured this entire acquisition to take RPM pulse train and convert that to angular velocity. So as you can see here, we've got a number of different types of conversions that we can do, or physical measurements we can do. In this case, we want to convert the pulse train to angular velocity, and we've given it a range based on how fast we know we can spin here.
Yep.
And then we've also said, hey, my sensor is spec'd to generate 120 pulses per revolution, and I also want to enable a feature on that module through the configuration to say, hey, I do want that 5-volt pull-up resistor, and the threshold is going to be TTL.
So a lot of configuration menus that will walk you through your measurements.
Right.
Like depending on what kind of sensor you've got, there's a configuration pane for it.
Right. And so now I can see live channel data on that conversion. I can see it spin up. I can see what the frequency is for raw. And
even in the configuration pane, you can do a little debugging and testing.
I can make sure that looks good.
That's great.
Cool.
Now, while we're talking about doing things live, you mentioned earlier when you were on the front panel on the screen that you were showing instantaneous Gs coming off of that sensor. What if we wanted to swap that out with like an RMS calculation?
Yeah,
let's walk through that.
Let's add that. So we mentioned no code. One of the values here is I can do some of these more fundamental calculations with simple configuration.
Yes.
So I'm going to add an RMS channel, and I'm going to map it to my instantaneous acceleration, right? So I've got, let's go down here to my 9234.
So all your channels are in that tree.
Right. I can see all the physical channels as well as my local variables and my local calculations, and I can reference those in other calculations. So in this case, I'm going to select my motor vibration. And now I can configure how long I want the block size, and now I can see RMS acceleration there. So now if I want to add that to my front panel, I can just simply go in here, right click, and let's map that to an indicator, a numeric indicator. Let's look at that here. So you can see I just did RMS. I can type that in the search.
Yep.
Add that here, and now I've got RMS acceleration.
So this was another example of a good idea. I'll call it a good idea. It might have been mine, but we wanted to add an RMS calculation to the screen. Right. And not only could we say, yes, we could do that, but it was obviously pretty straightforward. You just did it in a matter of minutes.
Right. Very quick.
Okay. Let's zoom out a little bit. Let's have some more good ideas. Let's say that we're testing more than just one product, and we've got a bunch of different test stations in a lab.
Right.
Let's talk about viewing multiple test stations or data from multiple test stations at once.
Right. So first, before we do that, let's build up the context of why you might want to do that. Aside from having all these different test cells, one of the things you might, this is built for interactivity, right? I want to put my hand on the drill.
Oh, yes.
In reality, I want to automate this system. I might want to automate things like pulling the trigger or changing modes on the drill or applying the brake or all of the above.
Yep.
And in those cases, if it's automated, I don't need to be standing here in the lab at my test cell. So I really want to also not only see my fleet of testers, but I want to be able to look at that on a dashboard or maybe remotely at my desk and go do other work.
Perfect example.
Right? So one thing that's cool about FlexLogger, in the vein or in the spirit of configuration, one of the cool things you can do is I can enable pushing all of my physical channels and my calculations as tags to SystemLink. Yep. And that's, you can see here, I'm doing that with a simple configuration and asking it, hey, push all those channels up as tags. Once I do that, now I can create something powerful like a FlexLogger tile dashboard.
Yes.
So in this case, what you're seeing is a whole slew of tiles that I've attached to channels that FlexLogger is exporting. So as an example, let's say I want to add a new tile. I'll show you how quickly I can do that.
And we're still in the configuration world where you are checking boxes to enable data to move and just drag and dropping widgets to build a dashboard.
Right. And so FlexLogger is going to publish that for me, and I can add, let's say, another numeric tile. And from here, I can go in and see all of the channels that FlexLogger is publishing. So I can go, let's say I want to see what that critical temperature limit was that I'm monitoring the battery and the motor with. I can add that here, and you can even see that it added the units for me as metadata from the channel.
Because it pulled it through. Because it
pulled it through as metadata. So now I can see that tile down here. It's updating live. There's my critical limit.
Very cool.
Okay.
All right. So this has been a great walkthrough of a test system and some really good examples of how all these good ideas, the NI hardware and software helps you say yes to them, whether it's pulling an RPM sensor off of a torque, adding an RMS calculation to a vibration signal, or looking at all of that data on a dashboard. All right, Jeff, thank you. I think that is a great example of a test system and walking through the different ways that NI hardware and software can help you say yes to all of your really good ideas for your test system.